Guys, hope all of us are doing great. Before we proceed, I'd like to kindly request our members to go to YouTube and search Honest Sciences and Mathematics TV channel. Subscribe and engage us on the comment section, and also ring that notification bells to be getting updates on various topics we do in mathematics, physics, chemistry, and biology, and other related topics. So today we're going to look at the concept of the Carnot cycle. And of course, basically, we're going to be biased on the aspect of efficiency that are mentioned in our first discussion. So I said that from the Carnot cycle, this is going to be, of course, the consideration of an ideal gas that is subjected to a series of reversible changes. And I mentioned four basic processes in that specific case, which basically entailed isothermal and adiabatic changes, which basically entailed the concept of a compression and expansion in that specific order. So I mentioned that there are various stages which we are going to see specifically for the four stages of the Carnot cycle, whereby I said that if we consider the graph of this is entropy against temperature, we can be able to describe this Carnot cycle in these four basic series of course arrows that we can be able to illustrate this one. Whereby we said that the first case we're going to have this at temperature T1 and T2, and we said that we can be able to describe the four various processes of isothermal expansion and compression, and then adiabatic expansion and compression in that specific respect. Whereby we said in our first stage that this initial stage of isothermal expansion, this is going to occur at a particular temperature. We say that temperature 2, which is going to be regarded as constant, and there's going to be what we refer to as absorption of heat, given as a positive Q2. And in this specific process, of course, we have mentioned that the gas expands isothermally and reversibly at a high temperature, and of course, this is going to be accompanied by absorption of heat Q2 from a source. And the entropy of this specific system can be described as a ratio between Q2 and T1. And as we said, there's going to be a reversible process at this particular stage. But next, this is going to move to a second stage of adiabatic expansion, as we said, which is going to be adiabatic expansion at this specific stage, which is a process number 2. And in this specific process, the heat that is going to be involved in this particular case is going to be given as 0. And of course, this is going to be a state whereby the system is returning to this initial temperature of the sink given as T1. And we said that in this particular process, the change in entropy is going to be 0, since the value for Q is 0. And of course, that is going to describe that specific cycle of adiabatic expansion. And then next, we said that there's going to be another process of this specific arrow, whereby there's going to be change in entropy. And this is going to be the process of isothermal compression. And in this isothermal compression, we're going to have the negative Q1, which is the heat going to be, of course, involved in this particular case. And this heat is going to be released, of course, to the sink, or as the system goes to this initial temperature given as such. And therefore, we can represent the change in entropy at this particular point as negative T1 given as such. And then lastly, we said about, so this is going to be process 3. And then lastly, we said that we're going to have a adiabatic compression that is going to result in, of course, the temperature returning to its initial or starting point being given as such, and the entropy of this specific system is going to be 0, since the value for Q is also going to be 0. So this constituted what we refer to as the Carnot cycle. And in this case, we're going to use the Carnot cycle in trying to represent the concept of efficiency, which is, of course, our discussion in this particular video. So I'm going to have this one given as such. So as we said, the net heat that is absorbed, of course, can be represented in terms of, let's give this one as Q. Of course, that is going to be given as Q1 minus Q2. As we said, this is going to be the net heat that is absorbed And of course, this particular heat, as we said, is going to represent the work that is particularly done in this Carnot cycle. And of course, the efficiency of this particular engine can be described as a fraction, and therefore this is going to be given in terms of a fraction of the work done all over this specific heat that is taken into the system. So we're going to have efficiency given in terms of the work done over the heat which is taken into the system, as we said. So basically, I've said that the net change in heat, which is given as Q2 minus Q1, is going to constitute the work done, and therefore this is going to be given as the efficiency is going to be given as a ratio between the work done and Q2. So basically, we're going to substitute this particular aspect of the work done as Q2 minus Q1. Therefore, this efficiency can be given in terms of this Q2 minus Q1 over Q2. The total change in, of course, entropy. So I said that we had an entropy change for the first case given as Q2 over Q, of course, T2. And then we said that this is for expansion, isothermal expansion. And then for isothermal compression, we're going to have this one given as negative Q1 over T1 given as such. So the difference between the two, or the total, of course, entropy of the system can be described using these two specific aspects of isothermal expansion and isothermal compression. Since for the adiabatic system, we have said that the Q is equivalent to 0, so therefore the ratio for adiabatic expansion and compression is going to be 0. So the total change in entropy is going to be given as, let's assume this one is, so not basically assume, this is going to be entropy 2 and entropy 1. So this is going to be entropy 2 minus entropy 1, as we have been doing now various equations, which is going to be, of course, this is going to be the summation of this specific entropy of the system, which is S2 plus S1 in that specific case. So this is going to give us a Q2 over T2 minus Q1 over T1. So this should have an addition sign, but remember that for the concept of adiabatic compression, we're going to have negative Q value, and this is going to result in this. And we had said that the total entropy of the system is going to be given as 0. So this is total entropy. Therefore, this is going to be equivalent to a 0 value. Now, from this specific equation, we can describe this particular aspect of Q2, which basically is going to appear in this specific form from a relationship of the efficiency equation that I've given. So therefore, that one having been said, we're going to have this Q2 over T2 equivalent to Q1 over T1, and then Q2, we have this one, implying that Q2 is equivalent to Q1 T2 over T1 given as such. So for us, we can do a substitution of the value of Q2 from this specific representation, whereby we're going to have efficiency, just putting a symbol for that. This is going to represent efficiency. It's given as Q2 is given as that. So we're going to have Q1 T1 all over T1 minus Q1, and then we're going to have this one all over Q1. So this is Q1 T2 minus Q1 T2 all over T1, and then given as such. So this is going to be the ratio between Q2, Q1 given as such, and then this is going to reduce into the equation of the form. So this is going to reduce into the equation of the form efficiency represented by T2 minus T1 all over T2 given as such. So this basically is going to be the ratio between various temperatures for of course the two changes in temperature given as such, and that is going to give us our aspect of the efficiency in the Carnot cycle. And of course, this is going to, as we said, give the degree of conversion of heat into work. And this is one of the applications of the concept of entropy, which I had mentioned in our first description. So catch us in our next video as we're going to look at various other applications of the concept of entropy, enthalpy, and of course other aspects which are related, which we have done in some of our videos. And I'd like to encourage our members to kindly open the link that are normally put in our description boxes for various other discussions that we have on the same. So that is it for now, guys. Bye. God bless you. Catch us in our next video.